Hieu and I are going to present this evening about holistic multi-objective optimization in floating offshore wind, which sounds a bit buzzwordy, but hopefully as we go through the presentation, we'll try and give a bit of colour to what we want to talk about, and then happy to answer some questions at the end. A little bit of context for those that don't know about Atkins, S&C Leveland. We've been involved in the offshore oil and gas industry for the last 45 years, last 18 years in offshore wind, designed lots of offshore wind foundations, both fixed and floating, lots of integrity management and substations. So we've been in this space for quite a long time, and have done some cool projects over the years. And this is a bit of a presentation as to where we're at now and what we're doing at the moment. So I hope you find it interesting.
Yeah, just worth mentioning, we were co-developers for Kincaid floating wind, and we also completed a pre-feed and feed design for hexagon floating multi-wind turbine wind power platforms. Is a long word, but yeah, that's we have done quite a few floating projects so far.
Okie doke. So as we go through the presentation, we will start with some pretty high-level optimization stuff, and as we go, we'll bore down into some more relevant examples. So you know, talking about some of the bottom fixed offshore wind stuff, and then Hieu will talk about how we've applied it, and we are applying it for floating wind foundations. So let's crack on the next slide, Hieu. Right. So here we go. What is optimization? The way in which we use it is by having a process set up to allow us to explore the design space and really understand how the inputs to our project, whatever that project might be. It could be designing a hull, it could be the layout of a wind farm, it could be where you put your wind farm in the world, how the inputs and the decisions that you make at the beginning affect that, and it allows us to ensure that those decisions are made with as much knowledge as possible right at the beginning. Optimizing at the beginning of the project sounds like a slightly unusual way to do it, I think, but hopefully as we go through this, it'll become a bit clearer as to why we feel that starting your optimization process right at the beginning and using the tools and the techniques for optimization can really benefit your project. So we'll talk a bit about optimizations. You go on to the next slide, Hieu. Yeah. Right. So here's a super nothing to do with naval architecture example about multi-objective optimization. So we'll take this example of how we reduce our time in getting to work. That was when we actually went to work rather than just walked downstairs. So if you want to optimize your commute to work purely for time, you might fly a plane. Or if you wanted to choose the lowest pollution option, you might walk. There's lots of solutions in the middle, but what we want to find is the right compromise for us, which, as we're naval architects, might be a boat somewhere in the middle. But none of the options on screen are, or rather, we don't know how close to being optimal solutions they actually are. So we work to optimize them. So fire up the next, thank you. Yeah, here we go. We want to end up down in this bottom left-hand corner, which is the lowest pollution in the quickest time. So we can get faster planes to reduce the time, but they also increase the pollution. We can get better trains, we can get quicker boats, or boats powered by sails that are slightly better, nicer looking bikes, or we can run. But what we're trying to do in this optimization process is force our way down as close to this bottom left-hand corner as possible. And there's this concept that is the Pareto front, which is the line that defines how close you can get to your target area, and any design, whether it's a bike or a boat or a train, that is optimal will sit on that line. So it's really it's the furthest you can go to optimizing your design, and that's really what we're trying to push towards. But with a lot of how we do design in the offshore world is we don't quite know how close to that line we're at, and so optimization is, and the tools that we use for it is the sort of process by which we force our designs as close to the Pareto front and the theoretically optimum set of designs which sit on that line as possible.
Next slide, I guess.
Yeah, next slide. Okay, so here we go. What does it mean in terms of offshore wind? What we have here is perhaps lots of different objectives. So previously we were looking at two objectives. We had just pollution and speed, but there might well be a scenario where we have lots of different objectives. So in this one that we've got up here, we're looking at an offshore wind turbine, where you have mass, performance of the turbine, levelized cost of energy, capex, opex, fabrication time, installation window limit, local content, and risk. You might want to optimize your design to any one of those objectives. So you might, as the example in the dotty line here, you know, we've optimized something for performance, say that might be energy yield, but we can see that there is a significant effect that we've had, say, on local content, installation window, and fabrication time in this instance. And so our design, which is the dotty line, is a combination of all of it, but is optimized heavily towards the performance aspect of it. Multi-objective optimization is where we optimize not against just a single objective, but a number of them. And the red line here shows what our design could end up looking like if we optimized against a range of different objectives to get what we believe is a holistically more optimal structure than one optimized just against a single objective. So that's really what we're trying to achieve with multi-objective optimization is trying to cover off more than just a single base. And so I spoke earlier about when you might do this, and optimization often feels like the sort of thing that you might do at the end of a project once you've done detailed design, and then you pretty much know exactly what your structure is going to look like, and then you optimize it by, I don't know, grinding welds on a jacket or polishing it or painting it with go faster stripes or something. And that's I think often how people see optimization. It's the sort of the final frills, and it can be, but it's very difficult to actually change anything at the end of a project. I suspect everyone on the call now who's done detailed design knows, by the time you get to detailed design, if you want to make a change, it goes down really badly with everyone involved. And so it's really worth trying to understand really early on what the end game might look like, so that you're not trying to make changes later on which are extremely expensive. And so we would suggest that adopting optimization techniques earlier on in your project is well worth doing. You have much more flexibility to change the way that your design is going. You can you can have a 4-column semi-sub or an 8-column semi-sub or a 3-column semi-sub at that stage, which, things that you can explore that design space and really get to the bottom of the implication of these decisions early on. Whereas if you leave it until later in the project, it becomes significantly harder to make the changes, and the effect of the changes on cost and duration of the project go up massively. And so really it's this left-hand side of the graph, the sort of concept design stage and moving in towards feed, where you want to be really taking advantage of using some of these optimization techniques, because if you leave it till the end of the project to do any optimization, your options for changing anything are hugely limited. Yeah. So what are we going to talk about next? Okay, so we'll start looking at how we might be applying this into offshore wind structures designs. So here we go. Right, this is what a conventional design process looks like. I suspect you're all fairly familiar with this. As your naval architects, you'll probably have in your mind a spiral of some description for this process, but fundamentally, we have an initial design configuration. We do some analysis. We have a look at the results of the analysis, and we decide whether or not they meet our criteria. If they don't, we have another run at it. If they do, we've got a feasible design solution, and we have a look at it, and we look at the utilization ratios or the safety factors that we've got in our design, and decide whether or not we think it's efficient. And if we've got utilization ratios of 0.1, we might think, yeah, we could do better than that, and we go around the loop again. And if it's all at 0.9, we think, okay, that'll do, and we finish the design. That's a relatively simplistic, perhaps, but conventional design process. However, you get to the end of your design, and is it an optimal design? Not sure, really. It might be optimal against a single criteria, either by luck or by good judgment. But the real answer is we don't know how close to being optimal that design is, and it might be that it's a very, very highly optimized semi-submersible, but it's in too shallow a water to actually be floating. And so I think there's a real need in the offshore design world to know how close your design is to being optimal. So if we look at how we might optimize this, you go on to the next slide. Here we go. So really, what we're going to try and do here is take the design process that we know and understand, and wrap it up into a big design environment. And this process is how we go about defining what that Pareto front is, and looking at where and understanding the design space, looking at what designs are optimal and which ones don't really meet our criteria. So you pull your process into effectively a sort of an automated analysis environment, and there are lots of these that are commercially available. You can buy some software that does it. It's not a piece of software that Atkins have developed or anything like that. It's pretty off the shelf. If you're clever enough, you can do it in Excel. But really, it's about bringing everything into one place, and I suppose, firstly, automating this process, but then taking that automated process and using some relatively clever optimization algorithms to drive the design process so that it seeks out what your design space looks like, and hunts out the optimal designs within the range of inputs that you define. And so that's really what we would be trying to do with this process. We would be using an automated system to map out our design space with as many other things in as possible. So often you don't really care, all right, you do care about steel weight, take it back. You do care about steel weight, but the reason you care about steel weight is because of the cost implication on your project. And so you want to build cost models into your optimization routine. You want to look at the long-term operability costs of say your wind farm, because they all drive your levelized cost of energy, which is something that you particularly care about if you're developing a wind farm. And so these are all the factors and tweaks that you can make to your optimization process in your design environment that mean the results that you can look at and the data that you get out at the end can be really valuable to your project. So that's really what the sort of process for this multi-objective optimization needs to look like. It's not rocket science to say you can do it in Python, or you can buy some software to do it. But it's just something that we don't do very much of in the offshore industry, and I think in that sense we're quite a long way behind other industries. The automotive industry and the aviation industry do this sort of stuff all the time, and I can't speak for all naval architects. I suspect there are some that are properly good at optimization, but I think the offshore industry that I work in, we're not very good at this, and we're coming up the learning curve quite quickly. But it's something that I think as an industry we really should be doing a lot more of. So perhaps we'll go into a few examples now. Hieu, is that what the next slide is?
That's the next slide.
Right, cool. So here are some more, some slightly more palatable examples, and in a minute we end up in a floating one, which, as for naval architects, is much cooler. So here we are. For a monopile design, say there are lots of parameters that you need to vary when you design your monopile. There's how deep it goes, how long your cone is, how thick the monopile is. Obviously there are lots of things that you can't change, like the soil stiffness and the water depth, but they become fixed inputs. But there's lots of geometric things about your monopile that you can change. How do you know what the right changes are? You can play around with them in your analysis software. You can change an input, test it, have a look at what the output is. But it's very stepwise, and it's potentially very slow. If you were to build the process of monopile design, say, into your design environment, your optimization environment, then you can start to get some really interesting insights into your design, and you can look at how your solution, or rather look at how your initial decisions, something that's pretty fundamental, say the diameter of the monopile, you can start to see how that will affect, I don't know, perhaps say your natural frequency or the mass. And so this graph on the bottom right hand corner of the picture, we've got a few different monopile examples here with different mudline diameters, and we're looking at lots of dots. Each of those dots is a different design that our multi-objective design optimization stuff. We use a tool called Mode Frontier for that, but there's lots of designs that it's come up with. All of them are feasible. Not all of them are optimal, but you can see that Pareto front starting to form, which is the sort of top of the curve. And down at the, if you're sort of in the 12-meter mudline diameter monopiles, there's quite a limited range where they're considered optimal from a natural frequency and mass point of view. And as you move through to the heavier structures, you can understand how that's affecting your natural frequency, and use this to inform some of your early project decisions around things like, say, diameter or construction weights, or perhaps something a little bit more relevant, like, you might be looking at mudline diameter against levelized cost of energy, or OPEX costs, or something like that, something that has a real bearing on the project. But the key is you have all this data available, and by being able to view it, you're able to make some much better field development decisions up front. And that's really the key thing that we're looking at here. And we've done this recently. What we were doing it for some secondary steel, which is that the next slide?
Yeah,
I think it is. Yeah, so we were designing an external working platform for a monopile wind farm, and we had a design that we'd been working on a little bit. We hadn't been using multi-objective optimization for it, but we were just designing it, and we got to a design that us and the client were pretty happy with. Principally, it looked like the last one that they had made, which I think is what is in this picture. So it looked like the last one they'd made, so they were happy. We'd done the checks; it met all of the code criteria. Everyone was relatively happy. We then said, right, can we please try and optimize this? Can we sort of have another run at it, but use the optimization process rather than going down the more conventional design route that we had beforehand, which effectively involved sketching what they had beforehand and then doing some engineering for it. And we managed to save 45% weight on that external working platform. We still, it was still a feasible design. It was, but significantly lighter, and that then obviously has such a huge knock-on effect, not just in terms of the cost of steel, but in terms of the installation vessels that you're able to use to install it on the monopile, and all of that sort of stuff. So it can be really beneficial, and it has really sort of shown its worth, I think, and continues to do so. And often you will surprise yourself. I mean, we surprised ourselves a bit here in this example by saving quite that much weight. We were sort of thinking we might get 20%, but it just shows something that you thought was a pretty good design, because it's broadly what the last one looked like, and it meets all of the code check criteria without too much fat in it. You sort of feel like it's a reasonably good design, but actually it can be an awfully long way from optimal against what we consider in this instance to be the really important criterion, which is weight. So yeah, that was an example that we've used this for recently. That I think it was really beneficial to us and the client, and something that I think we should be doing a lot more of in the industry. Okay, right. So is it the one with the floating wind turbine next to you?
Yes.
Okay,
Alex, just want to add in here. People can still hear me speaking, right?
Yeah.
Okay, just want to be sure that I'm allowed, that people can hear. I just want to add one more point in here. So this is the optimization and using the same steel grade. So I think S355. If at the moment Atkins is also looking into using other extra high strength steel in a different part of floating wind for secondary, and then it shows that it saves a considerable more weight and even cost, because even though it's more expensive, the amount of weight that you can save is more, so it proves to be more useful to use extra high strength steel in a certain parts of secondary of floating wind. So now we move to the next slide. Right. Okay. So I start by optimal designs for floating offshore wind foundations. So I start by this slide to show various concepts of floating wind foundations. So to name a few, To name a few, you can see here, wind float, ideal damping pool, hexa float, G-Con, Fukushima, you name it, there's lots of them. So unlike bottom fixed offshore wind, where there's predominantly two configuration, jackets or monopiles, the floating offshore wind have seen numerous concepts, and each has claimed they have optimal design. So I think in the next few slides, we're going to share with you the process that they possibly have gone through to obtain those design. Right. So for floating wind, as you can see, there's a we put the column on the left for the design variables, and the column on the right is about design objectives. So just to provide a bit of a background, especially if people are not from the naval architect background. So for floating wind, a number of design variable has to be considered. The first and foremost is the hull form type, whether you would use a spar, a semi-sub, or a TLP, because it's a very important things to decide. And then once determining the type of hull type, for example, semi-sub, then you start to consider the column diameter, the column spacing, the overall dimensions, just the length, breadth, depth, and then go on to the ballast, the amount of ballast water, the structural scantling, and the mooring type. And then on the objective size, there's multi-objectives that you want to consider. You want the platform to be relatively stable with the smallest possible inclination, but that would means it has to be quite heavy, and apparently the owner, if you're owner, you want the weight to be minimum because it's proportional to cost. So that's already a contrary in objectives, and then more complex objectives will need to be considered. You want the natural period of the structure to be, as well as the eigenvalue natural frequency to be away from the wave energy, as well as the 1P and 3P of the turbine. So all of that has to be considered, and it can be very, very complex. Many design objectives. So where do we start? So interestingly, I would say to address a very complex situation, you can still use the same approach as in optimization problem as in bottom fixed offshore wind, but apply in the floating wind concept. So I would give a simple example so that everyone could understand. So for example, in here, as you can see in this simple example, we'll firstly try to vary the column diameter, and then the distance between columns, and then we run the intact stability, diffraction analysis, eigenvalue analysis, and then we look into whether it has positive GMT, where is that 1P and 3P, if it's a feasible design solution or not. If it is, and whether it's on the parietal front, and then we run optimization, and then we see the number of design results. I'll show in the next two slides one simple example with the two objectives, and the other example with three objectives to show what's the difference between them, so that you can have the feel of them. Right. So this slide shows the double objective optimization weight versus the inclination angle, where the two contrary objectives explained in the previous slide. And what we aim for is this, again, is this bottom left corner in here, where it has both lower weight and small inclination angle. The colors of the dots are the ID number, with a smaller number is where it starts, and then the and red moving to a red color is where it end up with. So you can see that the algorithm started with some random values along this map, and then quickly moving toward the parietal front. And in this case, we use Excel to calculate the inclination angle, and we managed to run 2,500 design points. So you can see it can get into the parietal front very critically, especially when it only has to deal with two objectives. However, in this slide, it's more complex, where we try to optimize with four objectives. So weight, Hieu natural frequency, the GMT, and then the there's the small one here is called a pitch natural frequency. So as you can see, as you can see in here, what we need to look for, it will also start with various points from this side, but it would not go to the parietal front of the Hieu natural frequency in width that quickly. And then the endpoints in here is not on the parietal front lines of these two objectives, because it also has to consider other objectives such as GM or pitch natural frequency in here. So in order, when it comes to 4 objectives, what you need to look for in here is something with red color in here, which is sort of GMT toward red color, so red or orange color, and it's has to be a circle and along this line. So with this tool for 4 objectives, you can see the area where you want to be is around that area. And then once with that 4 objective, we would not make the decisions for the owner. We would simply using this tool to visualize, and then we discuss with the owner which objective they will prefer to go for and which is not. And then just a slide to show the complex design space could be. That would be very challenging for someone to think of how to optimize those one. So that you normally have to visualize these complex design space to see the relationship between different parameters and see whether some parameters are dependent on the other, and you try to reduce the complexity. And then you can see how much weight each parameters would have on the output. So back to Ed, to the conclusions of these tools.
Yeah, okay, so I can sum up. So I suppose we've covered some pretty high level stuff around multi-objective design optimization, how it's done, what the systems sort of look like, and the kind of things that you might do it for, and talked about a few different examples, Monopile's external working platforms, and then Hieu's talking about some floating wind turbines. Sorry if you can hear my 2-year-old in the background. She's very excited about something by the other side of the door. But I suppose the examples that we've used here are actually quite narrow. They're focused on the design of structures. But what's really, I think, valuable in all of this is using it for all kinds of things that you don't necessarily think of. So, you know, I suppose we've used it recently to help with some of the ScotWind applications for different companies, looking at based on their criteria what the best offshore wind leasing site would be for them to be applying to. We've been using it for the layout of offshore wind farms. And, you know, I suppose perhaps more than just a turbine, but where you put them within your constrained area. And so there are so many applications to this, and it's really, you know, not something necessarily that just we're doing. I'm sure there are lots of other people that are doing this, but I think it's something that, yeah, our industry is perhaps coming slightly late to the party on, but there are massive opportunities to use these optimization techniques in our industry, and I think they're proving to be really valuable. So I'd really encourage you to go and have a look. And there's also quite a good paper that got written in Transactions of RENA last year by Paul Gallagher about this, if you want the details of it. We haven't gone into much of the really technical detail in this, for the principal reason that I don't know it. But if you want to go and get stuck in and actually look at some of the really technical details behind it, go and have a look at Paul's paper, because it's it covers it in a lot more detail than we have here, and so I'd really recommend that. And I think that's all we got.
thanks to James Hamilton, who's come in, and he asked the question, do you use curve fitting to any extent to simplify the optimization?
So I suppose, yes, I suspect is the short answer, though, to be honest, in our process that we do it, the optimization algorithms, you might have a bit more detail as to what they actually are pretty good at seeking out the optimal designs and exploring that design space, and so we don't really need to too much. What we do use quite a lot of kind of, I suppose, curve fitting for is to simplify some of the analysis. So we, using trends and stuff like that, so that we don't have to run significant batches of diffraction analysis, say at each design point, because that can become quite laborious. So there are some bits and bobs of that we use to simplify some of the stuff, but perhaps not purely from the optimization point of view.
Okay. Question from Ian Duff. Good evening, Ian. He asks, how do floating wind platforms compare with fixed ones in terms of performance?
Well, as a group of naval architects, I would say they're infinitely superior to the fixed bottom ones. However, at the moment, they're quite a lot more expensive than the fixed bottom ones, but have an awful lot more flexibility as to where you can put them. In terms of energy yield, they're broadly similar. There's not a significant detrimental effect because it's floating and moving around a little bit more. There is a little bit. There's a capacity factor, but generally, from a turbine operating point of view, they're not wildly different. Obviously, fixed wind turbines, you're pretty limited by water depth, and so at about sort of 60 to 70 meters, the fixed wind farms will become there'll be a crossover in the price, and it'll become cheaper to do a floating one in water depths over about 60 meters or 70 meters. But at the moment, floating is much less technologically advanced. It's much less technologically advanced, so it's a lot more expensive just at the moment, but the industry is catching up, and they should get closer on price fairly soon, we'd hope.
Well, I could speak a whole hour about floating wind versus bottom fixed offshore wind. There's a lot of things that we can say. Yes, at the moment, floating wind is quite more expensive. I think it's double as expensive. I just have something in my LTOE of bottom fixed around 30, or floating is about 60 pounds. That's just a rough number I have. But first thing, the Center of Floating Excellence, I think, just published a paper to say about the roadmap of how to drive down the cost of floating wind. And they believe that in about 2030, that the price of floating wind would go down to the level that there's no need for support from government. So I think it's a good sign, and we've seen that journey for bottom fixed. So it will be very similar for floating wind, and then there's a lot more advantage of floating wind that could be deployed later on with much bigger wind turbines. Which there's certain limits for bottom fixed. And then also one of the concerns for floating wind before was how you can transport the energy back to the shore. And now there's a lot of development for hydrogen, where you electrolyze water into hydrogen and pump it back. So there's quite a lot more and more people talking about floating wind and hydrogen. It's still focusing on the floating wind turbine and how you convert that into energy and bring it back. It depends on how close you are to the shore and the water.
Okay, thanks. A question, I guess, on a similar vein from Jerry McKirk, who says, so there's lots of different designs and they can't all be right, exclamation mark. There's optimized designs even for different environments. Which ones do you think are the best designs?
For floating wind? Well, I mean, I suppose it depends on so many factors. It depends on, you know, the water depth, the set of environmental conditions, the fabrication facilities that you've got nearby if you want to use local content. So I suppose that's sort of why we feel we need to engage with this process really early on in the design of your offshore wind farm, because each design configuration for a floating wind farm has its own benefits, and part of what we would use this process for is to help identify which the right design for a particular development is, and then how that design may be optimized given the constraints that you have at a particular site. So you're right, so some are better than others, and some might be optimal for very few sites around the world, and some might be optimal for slightly more. But there are a lot of dependencies, and it really principally depends on some of the developers' choices to some extent in terms of what they actually want on their site. It might be that they have a particular style in mind. You know, they might really like spars, in which case going down the route of a semi-sub doesn't seem like the right decision. Equally, spars wouldn't be great in fairly shallow water. So it depends very much on where you are in the world, but it's sort of why you'd want to engage this early, so that you can start working it out sooner rather than later.
Yeah, in terms of sort of prevalent designs, you possibly heard that there's only two types of floating wind that currently have on, not a demonstration, but pre-commercial. So one is a high wind for spar concept, and then the other one is the wind float concept for principal powers, which is quite well in the different projects nowadays. And there's some quite a few of them on demonstration project at the moment. In general, I could provide a view that spars are relevant for deep water, but also there's one disadvantage of spars being that in order you have to find a very quiet field to you pen it before you tow it to the place. So if they can solve that problem, then still there's other things you need. So at the moment, as I can see, different part of the world, they quite prefer a semi-sub concept at the moment, but things might change when there's some semi TLP or semi-spa getting on. So tetra spa concept would be a pretty good one. So there's quite a few of them, and we always working close with the client to see what they need, their preference, their locations are, and the site condition, in order to tell which one is the most suitable. I wouldn't say the best concept in there.
Okay, thanks, guys. Paul Gallagher, he says, can you say something about uncertainties in the input parameters? For example, soil stiffness or drag coefficients or damping?
So, yeah, okay. I think obviously there is quite significant uncertainty in a lot of the input parameters that we use for design. Using these multi-objective optimization techniques allows us to do some pretty good sensitivity analysis on our inputs for the design. So I suppose what we are able to do is use the process to explore the design space and understand the sensitivity of uncertainty in our inputs to the final design. And so yeah, it's a really useful tool for that. But in terms of your actual examples in there, I'm not sure I could. I can't tell you what the answer to those specific ones are, because I don't know off the top of my head. Principally because my colleague Ben put the slides together.
Okay. Daniel Tonrus asks, how large and powerful are the computers that you need for these types of optimization?
It depends on how complex a design process that you have wrapped up within your design environment are, but not that, we don't have that special computers. If each design you had to do a 10,000 panel diffraction calculation, then it would take quite a long time. But a lot of what we can do with this can be done without having to redo all of the analytical heavy lifting at every design. And so you can use some sort of hybrid or surrogate models in place of some of that kind of stuff to do a lot of the design iterations, and then do the bigger analysis on some of the once you've narrowed down in the direction you're going. So yeah, Dan, not mega computers, though. Given that things like Microsoft Azure exist now and are pretty easy to use, I think the computational limit that we have on the analysis PCs sitting under the desks are a bit of a thing of the past. Really, it's pretty easy if you do need to run a really complicated model through this process to do it on something like Azure or the Ansys cloud or something like that allows you access to some pretty powerful computers quite straightforwardly. So it's not really something that's caused much of an issue.
Okay. Dorothy Book Standard asks, how much engineering effort will go into validating a design along the frontier?
Quite a lot, as much as would go into validating a normal detailed design. So in this process, I suppose we can't pick one of the points that are defined, say, on our Pareto front. We'll say we'll have that one, and that's not a fully detailed design. It's what we believe is an optimal design, but you still need to do a lot of the engineering to prove it. You still need to go through the motions, run the full suite of load cases, do your standard code checks and all of that sort of stuff. So yeah, it's not it doesn't replace detailed design in any sense. You still got to go through that process.
Okay. Aijun Wang asked a question: to construct the surrogate model for the response model, how do you ensure the accuracy of the response model for such large numbers of design variables?
Okay, cool question. So we do use some surrogate models to simplify and speed up our process. I sort of mentioned diffraction analysis earlier, that we can use response surfaces as an alternative for that. But we don't typically have surrogate models that have all of the design inputs built into them to create that. A single surrogate model that will define the whole response surface. We would use simplified models to perhaps tackle some particular parameters, some particular response parameters of our structure, whatever it is. But yeah, typically we wouldn't have a 10 parameter response model as the core. We would stick with some of the more conventional, would have a stability model and a hydrodynamic model for the motions, and some structural models to work it out, but there'll be separate models all within the same design environment. So they'd all be interfacing with each other to produce a design, but it wouldn't be a single model that covered all of them, and particularly not a surrogate model.
Yeah, I think one of the cases we use surrogate model to help with the prediction and reduce the number of simulation that we have to run, but we would not trust it. That values we get in the surrogate model, we still run it to make sure that it's actually in there. And it's close, but it's not exactly that point. But yeah, never use surrogate model for the answer. It's only that for prediction.
Okay, thanks, guys. Robbie Collington asked the question, have you considered any potential benefits of incorporating machine learning into the optimization process?
So feels like it's your bag, this one, Hugh.
No, it's interesting. People mention that optimization method in there is already used machine learning inside. So I've asked the developer of one of the tool when asked him if he've used machine learning, and he said he wasn't sure. But when I read the background of how the tool was built, it has a machine learning inside. They're building the surrogate model, trying to optimize all these things in there. It was already part of the machine learning process. So it's not as much as AI where you put in there and ask it to optimize for ourselves, but all of the mathematic models they use in there, all of the algorithm that they use has built-in machine some part of machine learning.
Okay, thanks, Julie. You've obviously had the same thought and you've sourced the answer, so that's great. Jonathan Morley asked the question, are there more constraints on turbine size on floating compared with fixed?
So there's not really a hard constraint at the moment. The floating turbines that have gone out there have smaller turbines on than the latest fixed, but that's just because they're slightly further behind the curve at the moment. I think the long-term view is that floating turbines will be able to take bigger turbines than the fixed ones by virtue of the simpler integration process with the hull and the turbine, which can typically be done alongside rather than as an offshore operation. And so I think a long way down the line, floating should be able to take bigger turbines than the fixed foundations, but at the moment fixed certainly have bigger turbines than those on floating substructures.
I think in terms of constraint, it's just sort of we can talk a bit about difficulties that floating wind has. I think the main difficulties now is about if we have a floating offshore wind farm far away from shore and we need a floating offshore substation, then that the dynamic cables for export cables is still in research. I think there's a few research being done, but not yet published about that part. So at the moment for the demonstration floating wind project, they just get the cables directly from the floating wind to shore, but not through a floating offshore substation. So I think that's something that being developed at the moment. But if that can be solved, then I think it's ready for. Okay. Yeah, that's ready for commercial. I would say, yeah.
Okay, we've just got a couple of questions to go. The next one's from Bertie Wycombe, who asks, what impacts do you find that hydrodynamic responses have on wind turbine load factors, and how do you model this in your optimization analysis?
So I've just noted Ed has gone away. Yeah. So yes. So at the moment we will have hydrodynamics. So all the way loads on. We have uncoupled more analysis. And there at the moment we haven't managed to run fully coupled analysis to consider all of the impact from waves and wind in there. Because that would be more considered in the detailed design. So wouldn't be answered you fully at the moment, unfortunately.
Okay.
Sorry, I'm back. Sorry, Hugh, my computer had a meltdown.
Yeah,
absolutely. I think that the integrated coupled analysis we haven't built into this process yet, because it's quite a significant analysis on its own, and so doing it as part of the multi-objective optimization would be quite time consuming from our perspective. So it's not something we've really looked at yet, but it'd be quite interesting to do.
Okay, that's fine. Andrew Henderson asks, what do you think about horizontal tow out of spar buoys?
It's not something I've thought about too much. But yeah, you know, I think to some extent, why not? It removes quite a lot of the complexities with towing a spar in terms of draft limitations to the tow route. So yeah, I can't see why you wouldn't. The issue is you'd then be doing your turbine and spar mating operation offshore, which will require some quite high hook height, heavy lift vessels, and that's often quite an expensive process. So it would be it's much more preferable from a cost point of view to try and do as much of that lifting and integration of the structure and the turbine as close to shore or ideally alongside the quayside as possible.
Yeah,
and
I
so
think,
yeah, go on then, Hieu.
Sorry, I just say I think I've seen a concept where they have the vessels and then they have the turbine with the spar and the turbine already installed in there, but there will be other issues with that in terms of how high the hub height should be, and then whether there will be wave impacts on the blade and other stuff. So either way, you face some issues. So if you don't have the turbine already attached to the spar, then you have problem with install it on site. And if you have it attached, then you have to deal with the wave impacts when being transported.
Okay, thanks. Mary Zagaritu asks a question. I think you actually covered this in one of the slides, but maybe she came in late. It says, what other ways other than weight reduction can be considered to achieve optimization of the platform?
Well, I suppose there's loads of stuff. It might be that, you know, I think cost is always quite a big goal. Everyone wants it to be the cheapest, not necessarily, but lightest doesn't necessarily mean cheapest. It often is quite well linked. But yeah, there are loads of things that you can change to optimize your platform, and it may be weight, or it may be that you're optimizing to maximize energy yield, which for a floating wind turbine might be to reduce motion. So it might be that a heavier floating platform may move less, therefore the turbine performance is affected less by the motion of the platform and your energy yields higher. So it may be that that's something that you optimize against. Or it might be that if you had a very light platform, it could be extremely intricate and difficult to fabricate, so only be able to be created in a few shipyards in the world, and that may come at a premium cost. And so there's lots of different things other than purely weight that we could optimize against to I suppose end up with the right hull for a particular project. But you know, if you happen to be developing a wind farm that's right next to a very capable shipyard, it would make sense for your structure to be optimized against their processes, because it would save you an awful lot of hassle down the line with having to transport them across the world, or just tow them out from the site. So yeah, it's very project specific, really.
Okay, great. I'll go to the final question from James Hamilton, who says, floating structures often yaw at the slow drift period. Is this an issue for the turbines?
Not so much. Not at the slow drift period. You know, if we're up in the 1 or 2 minute type area, the controllers and the yaw motors can respond relatively well to that sort of period of motion. Where they aren't able to respond would be at the higher frequency, lower period motions, you know, sort of, I suppose, wave frequency yaw, it wouldn't be able to they typically counter that, and can't really do much about pitch and roll. But yeah, for drift frequency yaw, it's the controllers and the yaw sort of bearing and on the nacelle can keep up with that if needs be. But there's an argument that if it's only a moderate magnitude of your motion, it might be that it never really leaves the tolerance for the alignment of wind direction to actually warrant activating the yaw motors, and it'll just generally follow the change in wind direction.
Okay, thank you, guys. Thank everybody for your questions. I think that's added nicely to the presentation. Again, thanks for Ed for coming in to answer all those questions. I'm sure you've enjoyed it. And thanks, of course, to you, Lee, who set up the presentation for us. And thanks for Jamie in headquarters for coordinating the event.